Welcome to Sleepy Stories. It's good to have you here tonight. Before we begin, give yourself permission to slow down. Maybe you're already in bed, lights low, a soft hum somewhere in the background. Maybe you're on a couch or a train or lying awake with the quiet glow of a phone beside you. Wherever you are, nothing is required of you. Just listen, breathe, and allow your mind to follow a steady current of calm thought. If sleep arrives soon, let it. If it takes a little longer, that's perfectly fine. Even without closing your eyes, you'll drift through something real, something worth knowing, the steady, patient movements of the universe itself. If this way of learning helps you relax, a like or subscription lets us keep creating more nights of calm curiosity for you and others who need a gentle way to rest. Tonight, we begin with the galaxies. They are the great cities of the cosmos, vast assemblies of stars, planets, gas, dust, and invisible matter. The Milky Way, our home galaxy, holds hundreds of billions of stars and is just one among countless others. Each galaxy travels through space, pulled and guided by gravity. Though the distances between them seem impossible to cross, gravity works everywhere, quietly shaping motion on every scale. Over immense stretches of time, these forces can bring galaxies together. The word collision might sound violent, but in astronomy it means something different. When galaxies meet, they do so in slow motion. Each is mostly empty space. The average distance between stars is so enormous that almost none ever strike one another. Instead, the galaxies pass through each other, their shapes distorted by gravity, their gas clouds compressed, and their paths altered. What looks like a crash is really an intricate gravitational negotiation. The encounter may last hundreds of millions of years, ending not in destruction but in transformation. Astronomers observe these events through telescopes that see in many forms of light: visible, infrared, radio, and X-ray. Photographs of colliding galaxies show long arcs of starlight stretching outward, bridges of gas connecting two luminous cores, and clusters of new stars shining where clouds have been squeezed together. The antennae galaxies, the whirlpool galaxy, and the mice galaxies are among the best-known examples. Each one shows a stage in this slow choreography, revealing that collisions are common and fundamental to how galaxies grow. Inside each galaxy, gravity keeps the stars orbiting a shared center of mass. When two systems begin to interact, that balance changes. The combined gravity of both galaxies pulls stars into new paths, while tidal forces stretch their outer edges. Gas and dust respond more dramatically, folding and colliding, triggering bursts of star formation. After billions of years, the two galaxies may merge completely, forming a single, larger structure, often an elliptical galaxy that carries the blended history of its predecessors. At the heart of nearly every large galaxy lies a supermassive black hole, millions or billions of times heavier than the Sun. During mergers, these central black holes spiral toward each other, eventually combining into an even larger one. The energy released in that process sends ripples through space-time, known as gravitational waves, faint signals that scientists can now detect with remarkable instruments. Understanding galactic collisions helps scientists trace the evolution of the universe. By comparing simulations to real observations, astronomers learn how galaxies form, how star populations age, and how dark matter shapes the large-scale structure of space. Each collision is a chapter in the long story of cosmic development, not random chaos, but the natural result of gravity acting over immense time. As you listen, let that idea rest with you. The same force that keeps your feet on the ground is the one that guides entire galaxies through the dark. Nothing in the universe is truly still. Everything moves, shifts, and eventually finds balance again. You can let that thought settle, as constant and reassuring as the pull of gravity itself. A galaxy is not a single object, but a system bound together by gravity. Each one contains hundreds of billions of stars, vast clouds of gas and dust, planets orbiting unseen, and a halo of dark matter that outweighs everything visible. The structure of a galaxy depends on the balance between rotation, gravity, and the motion of matter inside it. When astronomers describe a galaxy, they often talk about three main parts: the central bulge, the surrounding disk, and the halo. The bulge is a dense region of older stars. The disk holds spiral arms where gas clouds create new ones, and the halo extends far beyond what telescopes can easily see. The Milky Way, our home galaxy, is a spiral type about 100,000 light-years across. It turns slowly, taking more than 200 million years for the Sun to complete one orbit around its center. That center holds a supermassive black hole called Sagittarius A*, whose gravity helps anchor the motion of the entire system. Around it, stars orbit in ordered patterns like traffic on circular roads. Beyond the bright arms lies a faint spherical halo, where ancient stars and invisible dark matter form a gravitational shell. Not all galaxies share this shape. Some are smooth and oval, known as ellipticals. They contain mostly older stars and little gas, which means they no longer form many new suns. Others are irregular, asymmetrical, stretched, or fragmented, often because they have been pulled or twisted by nearby galaxies. These differences are clues to each galaxy's history. Spirals are often still active, rich in gas and dust, while ellipticals tell stories of past mergers that used up their raw material. Dark matter plays the hidden role that keeps galaxies intact. Though it cannot be seen directly, its gravity reveals itself through motion. Stars in the outer regions of galaxies orbit faster than visible matter alone could explain. That extra pull comes from dark matter distributed in a halo much larger than the luminous parts we can observe. Without it, galaxies would fly apart. Understanding this structure is essential before talking about collisions. When galaxies meet, the visible stars are only part of the story. Their dark matter halos collide first, setting the gravitational framework that determines how the rest unfolds. The shapes we admire in astronomical images, graceful spirals, arcs, and streams, are surface expressions of deeper, invisible physics. Astronomers study these forms using light across the spectrum. Radio telescopes map hydrogen gas, infrared observatories look through dust to find young stars, and optical telescopes capture the glow of older ones. Together they build a complete picture of how a galaxy lives and evolves. Every wavelength adds a layer of understanding, much like different instruments in an orchestra combined to play a single piece of music. Thinking about galaxies this way changes perspective. They are not distant decorations scattered through space, but organized systems governed by the same physical laws that apply everywhere. The gravitational equations describing how the Moon orbits Earth also describe how billions of stars orbit a galactic core. Scale changes, but the principle remains constant. Matter follows curvature, energy follows gravity, and structure follows motion. As you picture a galaxy now, imagine not a blur of light but a complex, balanced system. Stars in predictable orbits, gas slowly cycling through birth and decay, and an unseen halo holding everything together. This understanding will become the foundation for what comes next, why these enormous systems move, and how their paths sometimes lead them toward each other across the silent reaches of space. Every galaxy you can see, and even the ones you cannot, is in motion. Nothing in the universe is truly at rest. The motion of galaxies arises from two large-scale processes: the overall expansion of space itself and the local gravitational pulls among massive systems. These two influences act together to shape the pattern of movement across the cosmos. Understanding both reveals why galaxies seem to drift, gather, and sometimes collide. Astronomers describe the expansion of space through the Hubble-Lemaitre law. The greater the distance between two galaxies, the faster they appear to move apart. It is not that galaxies are flying through a pre-existing void, but that the space between them is stretching. The galaxies are like points painted on an inflating balloon. As the balloon grows, each point moves away from all the others, even though none is traveling across the surface. This expansion began after the early universe cooled enough for matter to form, and it continues today on the largest scales. Yet not all galaxies follow that general outward drift. Within clusters and groups, gravity can overcome expansion and hold galaxies together. The Milky Way and the Andromeda Galaxy belong to such a gravitationally bound group, the local group, which contains dozens of smaller systems. The mass of these galaxies and their dark matter halos creates a shared gravitational field strong enough to resist the stretching of space around them. Inside such regions, galaxies orbit one another, sometimes in stable configurations and sometimes on slow collision courses. Motion can be measured through light itself. When a galaxy moves away, the wavelengths of its emitted light stretch slightly, shifting toward the red end of the spectrum, an effect called redshift. When it approaches, the light compresses, shifting toward blue. By studying these changes, astronomers can determine a galaxy's velocity along the line of sight. Instruments on Earth and in space can measure differences of just a few kilometers per second in galaxies millions of light-years away. This precision allows scientists to map the flow of matter through the universe like ocean currents across a dark sea. Galactic motion also carries traces of past events. Collisions leave long streams of stars and gas extending from galaxies, evidence of gravitational tides at work. Even when galaxies have separated again, those trails reveal the path they took and the forces they felt. Computer simulations can recreate these histories, confirming that the observed shapes and speeds match what gravity predicts. The motions we observe today are the current stage of an unbroken process that began billions of years ago and will continue long after our own era. Rotation adds another layer to this movement. Each galaxy spins around its center, a motion maintained by angular momentum inherited from the cloud of matter that formed it. Stars in the inner regions orbit faster than those far out, but all follow predictable paths determined by mass distribution and the pull of dark matter. This rotation gives galaxies their stability and their familiar flattened shapes. When two rotating systems approach each other, their spins interact, twisting and warping the combined structure into new forms. To imagine these scales, think of the Milky Way moving through space at roughly 600 kilometers per second, relative to the cosmic microwave background, the faint radiation left over from the early universe. The entire local group drifts toward a larger concentration of matter called the Virgo cluster. Beyond that lies an even greater pull, the Laniakea supercluster, a network of thousands of galaxies tied together by gravity. Every motion, large or small, follows the same rule. Mass attracts mass, and over time, attraction reshapes the landscape of the cosmos. This continuous motion is what makes collisions possible. Galaxies travel through space like ships on a vast, curved sea. Their paths, though determined by physics, are anything but static. When trajectories intersect, they do not stop or rebound. They merge and transform. Understanding why galaxies move allows scientists to predict when such meetings will occur and what they will become afterward. As you consider this, let the idea settle. Motion is the normal state of everything. The stillness you feel here on Earth is relative. Beneath it, our planet spins. The solar system orbits the galactic center, and the galaxy itself streams through space. Movement, not rest, is the universe's baseline rhythm, steady, precise, and endlessly unfolding. Gravity is the architect of structure in the universe. Every planet, star, and galaxy owes its existence to this single, consistent force. It is weaker than the electromagnetic or nuclear forces on small scales, yet because it always attracts and never cancels out, gravity dominates wherever enough mass accumulates. To understand why galaxies move, merge, and reshape, we must understand gravity not only as a pull between objects, but as the very geometry of space itself. In classical physics, Isaac Newton described gravity as an invisible attraction between masses. His equations predicted planetary motion with remarkable accuracy, showing that the same rule governing an apple's fall also governs the orbit of the moon. Centuries later, Albert Einstein expanded that view with his general theory of relativity. Instead of a force acting across distance, gravity became the curvature of space-time caused by mass and energy. Objects follow the straightest possible paths through that curved geometry, which appear to us as orbits. Both views lead to the same practical result. Matter moves toward concentrations of mass, and in doing so, forms larger and more complex systems. Galaxies are prime examples of gravity at work on cosmic scales. Each one forms when regions of slightly higher density in the early universe attract more matter. Over time, those regions grow, pulling in gas and dark matter until stars ignite within them. Once formed, A galaxy's gravity maintains order among its components. Stars orbit near the plane of rotation, gas clouds spiral inward, and the outer halo binds everything together. Without gravity, there would be no galaxies, no stars, and no stable structures at all, only a diffuse fog of particles drifting apart. When galaxies interact, gravity becomes both sculptor and storyteller. As two massive systems approach, their mutual attraction distorts their shapes, pulling out long filaments of stars and dust. These are tidal effects, similar to the way Earth's oceans bulge under the pull of the moon, though on a scale measured in hundreds of thousands of light years. The stronger the gravitational difference between near and far sides of a galaxy, the more dramatic the distortion. Astronomers can calculate these effects precisely. They are signatures that reveal mass, distance, and relative motion long before direct contact occurs. The same principle explains why the Milky Way holds the Sun and its planets in steady orbits. The Sun's gravity dominates locally, keeping Earth bound at a distance where light and warmth sustain life. Yet on larger scales, the Sun itself orbits the galactic center because the combined mass of billions of stars curves space around it. In this hierarchy of motion, smaller systems are nested within larger ones, a solar system inside a galaxy inside a group, and a group within a cluster, all governed by the same rule. Dark matter magnifies gravity's influence. Although invisible, it provides most of the gravitational mass in the universe. It gathers into halos around galaxies, extending far beyond the regions where stars shine. These halos interact first when galaxies draw near, setting the stage for the visible drama that follows. Simulations show that without dark matter, galaxies would be too fragile to survive encounters. Their stars would drift away rather than merge into new configurations. Gravity, strengthened by dark matter, ensures that collisions end in union rather than dissolution. Scientists measure gravity's reach through its effects rather than direct observation. Orbital speeds, lensing of distant light, and the movement of galaxy clusters all trace the invisible curves of space. Instruments such as the Gaia satellite chart stellar motions within the Milky Way, while gravitational wave detectors capture the faint ripples produced when massive objects like black holes coalesce. Together, these observations confirm that gravity links every scale of the cosmos into a coherent whole. Thinking about gravity brings perspective. The same principle that holds a pen to a desk binds galaxies across millions of light years. It is a reminder that the universe operates with consistency, from the smallest stone to the largest cluster. When two galaxies finally meet, it will not be by chance but by this inevitable attraction, the quiet rule that turns matter into form and motion into harmony. As you let that thought rest in your mind, imagine the universe not as empty space, but as a web gently shaped by gravity's hand, connecting everything that has ever existed. Galaxies come in many shapes, sizes, and personalities. Their appearance reveals much about their age, motion, and past encounters. Astronomers classify galaxies into several main categories: spiral, elliptical, lenticular, and irregular, a system that helps organize the vast diversity of forms observed across the universe. Each type tells a story written by gravity, time, and the flow of interstellar matter. The best-known example is the spiral galaxy, to which the Milky Way belongs. Spirals are graceful, disc-shaped systems with arms that wind outward from a central bulge. These arms are regions where gas and dust collect, forming new stars that make them shine brightly in blue and white light. The bulge in the center holds older, redder stars, and often a supermassive black hole. Spiral galaxies also contain a thin, flat layer of gas that rotates smoothly, maintaining the pattern of their arms through the interplay of gravity and motion. Roughly 2/3 of known galaxies share this design, making spirals the most common form in the visible universe. Elliptical galaxies, by contrast, are rounder and less structured. They range from nearly spherical to stretched oval shapes. Their stars move in random orbits rather than the organized rotation seen in spirals, giving them a smoother appearance. Ellipticals contain little gas or dust, meaning that new stars rarely form within them. Most of their stellar populations are old, ancient suns that have burned quietly for billions of years. These galaxies are often the result of mergers, the settled remnants of past collisions that blended two or more systems into a single, massive whole. Between spirals and ellipticals lie lenticular galaxies, which have disc-like shapes but lack pronounced spiral arms. They represent a transitional form, systems that once contained gas and star formation but have since exhausted their supply. Lenticulars bridge the visual gap between the vibrant spirals and the calm ellipticals, showing how galactic life cycles progress over cosmic time. Irregular galaxies defy symmetry altogether. They appear distorted, clumpy, or stretched, often because they are being tugged by the gravity of larger neighbors. Many irregulars are small dwarf galaxies caught in the process of being absorbed by bigger systems. Their chaotic shapes make them valuable laboratories for studying how interactions trigger bursts of star formation or strip gas from smaller systems. The large and small Magellanic Clouds, visible from the southern hemisphere, are nearby examples orbiting the Milky Way, companions that show signs of past and ongoing gravitational influence. This classification scheme, originally developed in the early 20th century by astronomer Edwin Hubble, is not a strict evolutionary ladder but a convenient map. A spiral galaxy does not automatically become elliptical, yet collisions and environmental effects can transform one type into another. For instance, two spirals that merge typically form an elliptical because their ordered rotation is disrupted during the collision. The variety we see across the sky represents different stages of galactic history playing out simultaneously. Dark matter again underlies these differences. A galaxy's halo determines how tightly it can hold onto gas, how fast it rotates, and how it responds to nearby gravitational disturbances. Denser halos can preserve spiral structure longer, while lighter ones are more easily distorted. Thus, the invisible framework of dark matter quietly shapes the visible diversity we observe. Galactic classification also helps scientists trace large-scale structure. In galaxy clusters, ellipticals dominate the crowded cores where collisions are frequent, while spirals are more common in the quieter outskirts. This spatial pattern reflects the role of environment in galactic evolution. The more interactions a galaxy experiences, the more likely it is to lose gas and settle into an older, rounder form. Those far from cluster centers remain active and star-forming, preserving their spiral shapes for longer. Understanding these categories prepares us to examine what happens next when two of these systems approach one another. Each structure reacts differently under stress. A spiral's arms may stretch into long filaments, an elliptical may absorb another system without much distortion, and an irregular may be completely reshaped. In the next stage of our story, these differences become crucial to predicting the outcome of galactic encounters. For now, it's enough to recognize that variety itself is a record of motion, a visible imprint of cosmic history captured in shape and light. When galaxies begin to move toward one another, the first stage of their meeting is almost imperceptible. They may be separated by hundreds of thousands of light years, yet gravity has already linked them in a shared future. Their mutual attraction grows slowly, reshaping the motion of stars and the paths of invisible dark matter halos, long before the galaxies themselves appear to touch. What happens next unfolds so gradually that even if you could watch for a lifetime, you would see no change at all. Astronomers call this period the first encounter or initial approach. Computer models show that two galaxies begin by exchanging tidal forces, uneven gravitational pulls that stretch their outer regions. The effect is similar to the way Earth's oceans bulge under the influence of the Moon, though on a scale so vast that the comparison almost feels abstract. These tidal effects draw out thin streams of stars and gas known as tidal tails. At first they are faint, nearly invisible arcs. Over time they lengthen, forming luminous bridges between the galaxies as material flows from one system to the other. No collision in space happens quickly. The two galaxies may take hundreds of millions of years just to halve the distance between them. During that time, the smaller of the pair often suffers the greater distortion, its shape pulled into elongated strands. Gas inside each system begins to compress in certain areas, setting the stage for new star formation when the galaxies come closer. Every step is guided by gravity's quiet arithmetic, a steady exchange of energy and momentum that cannot be hurried. For astronomers, observing this process is like reading the first chapter of a long novel. Telescopes such as Hubble and the James Webb Space Telescope capture pairs of galaxies caught in these opening moments. Some appear as overlapping disks, others are separated by dark lanes filled with dust and glowing hydrogen. By studying their relative velocities and the faint distortions in their shapes, scientists can reconstruct the sequence of events leading to eventual merger. Each image is a snapshot in a drama that has no single frame fast enough to reveal motion, only evidence left behind in structure and light. The galaxy's dark matter halos play a crucial role throughout this slow encounter. Though invisible, they begin to blend at distances where stars are still far apart. The overlapping halos create a larger gravitational well, drawing the systems together more firmly. Inside these invisible boundaries, gas clouds start to respond, heating slightly as they are stretched and compressed. In these early stages, no stars collide, no destruction occurs. Instead, the first hints of creation begin. Pressure increases, density rises, and future star-forming regions quietly take shape. It's at this point that the scale of time becomes most striking. The speed of light, the fastest thing known, would take millions of years to travel across the changing space between these galaxies. The processes that guide them do not rush. They proceed with the precision of physics, untroubled by urgency. Thinking about this kind of patience can be oddly comforting. In a universe that never sleeps, change still happens at a pace so calm that even eternity seems unhurried. If you're still awake, this story whispers, you don't need to chase rest. Let your breathing match the rhythm of galaxies drawing slowly together. Just as their motion continues without effort, your own thoughts can settle naturally. Sleep, like gravity, is not forced. It simply arrives when conditions are right. The first stage of a galactic collision ends when their outer edges finally interlock. By then, tidal tails have stretched into long luminous ribbons, and the galaxies are bound beyond escape. What follows will bring transformation, not destruction, a process where gravity, time, and motion cooperate to create something larger and more stable than either galaxy alone. After the first long approach, the galaxies finally come close enough for their visible structures to interact directly. To the human eye, it would look like a slow, silent meeting between two luminous spirals suspended in darkness. Yet what appears serene hides immense forces at work. Each galaxy feels the other's gravity pulling at billions of stars, bending the paths of gas clouds and distorting its original shape. This is the first true encounter, a turning point where their futures become inseparable. Astronomers describe several stages in this process. The first is tidal distortion, when the mutual gravitational pull stretches both galaxies, especially their outer arms. Material begins to flow outward, creating bridges of stars that connect one galaxy to the other. These structures are temporary. They will change and dissolve as the systems continue to move. Yet they are valuable clues for scientists, revealing the strength and direction of gravitational forces involved. The second stage involves gas compression. As each galaxy's motion stirs the other's interstellar medium, large clouds of hydrogen and dust collide gently, increasing density in some regions. This compression triggers waves of star formation, entire clusters igniting across tens of thousands of light-years. These new stars often shine in blue light, marking the most active and dynamic regions of the encounter. Astronomers can detect these starburst zones using infrared and ultraviolet observations, which penetrate the surrounding dust that often hides them from view. Meanwhile, the stellar populations themselves experience a kind of gravitational turbulence. Stars, though not colliding, begin to orbit in less predictable paths. Some are slung outward into extended arcs known as tidal streams, while others fall inward toward the growing center of gravity between the two galaxies. In this way, the interaction redistributes stars across vast distances, changing both galaxies' appearance. What began as distinct spiral disks becomes a tangled, luminous field of light and motion. Computer simulations have been essential for understanding this stage. By modeling the laws of gravity, scientists can reproduce what telescopes capture in single snapshots. Simulated galaxies can be rotated, paused, or rewound to explore every angle of the encounter. These virtual reconstructions reveal how long the interaction lasts and what the end result might be, whether the galaxies will merge into one or pass by each other and later return for a second encounter. In many cases, the first close pass does not end the story. It merely sets the trajectory for an eventual merger billions of years later. Energy transfer is another key feature of this process. When two massive systems interact, orbital energy gradually converts into internal motion, the same principle that governs the orbits of planets but scaled up to cosmic dimensions. As gravitational potential energy decreases, the galaxies become more tightly bound. Friction between gas clouds releases heat and radiation, which astronomers can detect as faint glows in radio and X-ray frequencies. This energy exchange marks the beginning of irreversible combination. Galactic encounters are not random collisions. They are predictable results of motion governed by gravity over immense spans of time. Even though the systems involved are separated by unimaginable distances, their paths follow the same physical laws that govern everyday motion on Earth. What looks like chaos is actually an expression of order, a universe obeying consistent rules everywhere, from the smallest orbit to the largest cluster. From Earth, astronomers observe dozens of such encounters at various stages. Some, like the antennae galaxies, display long, sweeping tails of stars stretching into intergalactic space. Others, like NGC 4676, nicknamed the Mice, appear frozen in mid-motion, their elongated shapes showing the aftermath of a close pass. These cosmic examples provide a timeline of interaction: the first approach, the tidal stretching, the creation of bridges and streams, and eventually the quiet merging into a single new structure. When you think of galaxies meeting, it's easy to imagine violence or destruction, but the reality is much gentler and more creative. The collision of galaxies does not erase what exists, it reorganizes it. Matter redistributes, stars find new paths, and gravity continues its endless work of shaping the universe into new forms. In the next stage, we'll see how this process, far from ending, becomes the birthplace of new light. When galaxies finally overlap, the encounter reaches its most dynamic stage. To human perception, the word collision suggests impact, explosions, or destruction. Yet in space, the distances between stars are so great that direct collisions almost never happen. What truly collides are the gravitational fields, the clouds of gas, and the trajectories of countless stars that begin to reorganize under shared attraction. It is less a crash and more a slow rebalancing of energy and mass, a cosmic reshaping rather than an end. As the galaxies interpenetrate, gravity begins to mix their stars. Each galaxy's motion perturbs the other's orbiting systems, causing streams of stars to stretch outward and bridges to form between them. These stellar bridges can span hundreds of thousands of light years, appearing in telescope images as pale arcs glowing softly against the black of intergalactic space. While most stars remain intact, their collective paths change. Some are flung far into space, creating extended halos, while others drift toward the newly forming center of mass. Gas clouds respond even more dramatically. Unlike stars, gas has viscosity. It can compress, collide, and heat up. When galactic gas clouds meet, they create shock waves that ripple through the interstellar medium. These shocks compress the gas, triggering bursts of star formation known as starburst events. Regions that once held scattered hydrogen suddenly light up with clusters of bright, young, blue stars. The energy released by these newborn stars illuminates the colliding galaxies, producing some of the most spectacular images in astronomy. Star formation, however, comes at a cost. Each wave of new stars consumes large amounts of gas, leaving less raw material for future generations. Over billions of years, this gradual depletion transforms a galaxy's character from a rich, star-forming spiral to a calmer, older elliptical. Collisions therefore act as both creation and conclusion. They ignite new light even as they prepare galaxies for quieter futures. At the centers of both galaxies, supermassive black holes play a hidden but crucial role. As the systems merge, the black holes spiral closer together, surrounded by swirling disks of gas and dust. These regions can glow intensely, forming what astronomers call active galactic nuclei. Energy from the infalling material radiates across the electromagnetic spectrum, sometimes outshining all the stars in the host galaxy combined. Eventually, after millions of years, the two black holes will coalesce into one, sending ripples through space-time, gravitational waves that carry a faint echo of the event across the universe. While these transformations occur, the galaxy's shapes continue to evolve. Spirals lose their neat symmetry, their arms stretched and twisted by tidal forces. Dust lanes cross and warp, forming temporary rings or elongated ovals. Over time, as the systems settle, these chaotic forms smooth out into a single, larger structure, often an elliptical galaxy with little remaining trace of the two original spirals. In this new equilibrium, stars orbit in random directions rather than orderly disks, and the remaining gas grows thin and diffuse. Astronomers have studied numerous examples that capture these stages in progress. The antennae galaxies show overlapping disks and bright regions of star formation, while NGC 2623 reveals a later phase where two nuclei have already merged into one. Observations at different wavelengths, optical, infrared, and radio, allow scientists to see both the hot, glowing regions and the cold gas streams that shape the future of these systems. Each example fits into the larger story of galactic evolution, confirming that collisions are among the primary engines driving change in the cosmos. The scale of time remains almost beyond imagination. From first contact to final merger may take 2 billion years or more. Every stage proceeds at a pace far slower than human perception, yet every motion follows the same laws of gravity and momentum that govern falling leaves, ocean tides, and planetary orbits. The universe operates by consistent rules, steady, predictable, and endlessly patient. To think of galaxies colliding is to realize how dynamic the universe truly is. Even in apparent stillness, everything is moving and interacting. These collisions are not catastrophic, they are essential. Without them, the universe would stagnate. Because of them, stars continue to be born, elements mix and recycle, and the grand architecture of the cosmos keeps evolving toward balance. One of the most striking outcomes of galactic collisions is the birth of new stars. When galaxies meet, their clouds of gas and dust are compressed and heated, turning quiet regions of space into active nurseries of light. These zones of creation, called starburst regions, can form tens or even hundreds of new stars each year, far more than the steady pace seen in isolated galaxies. What might sound like destruction is, in reality, a form of renewal on a cosmic scale. To understand how this happens, imagine the interstellar medium inside a galaxy, vast clouds of hydrogen and helium gas, peppered with tiny dust grains. In normal conditions, the gas remains diffuse and cool, spread too thinly for gravity to pull it into new stars. But during a collision, gravity and motion work together to compress the gas. As one galaxy's spiral arm passes through another, pressure waves ripple through the interstellar medium, forcing clouds to collapse under their own gravity. Inside these collapsing clouds, dense cores form, temperatures rise, and nuclear fusion ignites, the unmistakable birth of stars. Observations from telescopes such as Hubble, Spitzer, and the James Webb Space Telescope have captured these moments in detail. In some colliding systems, astronomers can see chains of brilliant blue clusters, marking areas of intense star formation. The antennae galaxies, one of the best-studied examples, glow with thousands of young, massive stars that formed in just the past few million years. Infrared images reveal hidden pockets of heat from newly formed stars, still shrouded in dust. These findings confirm that collisions are not cosmic accidents, but essential processes that rejuvenate the universe with fresh light. The physics behind these starburst events is well understood. When two gas clouds collide, they slow and compress each other. The resulting shock increases density, and once the pressure exceeds a critical threshold, gravitational collapse begins. Smaller fragments form within the cloud, each destined to become a star or a cluster of stars. Massive stars form quickly, burn hot, and live short lives, while smaller stars take longer to form and last for billions of years. Over time, stellar winds and supernova explosions from the massive stars push surrounding gas outward, regulating further star formation. In this way, collisions trigger not only creation but also feedback, a self-balancing cycle of energy and matter. Starburst regions can alter the overall brightness and color of a galaxy. Young stars emit more blue and ultraviolet light, giving colliding galaxies their characteristic glow in optical images. As astronomers observe galaxies at various stages of collision, they can estimate how long the starburst phase lasts, typically a few 100 million years before gas reserves thin and activity declines. Once the burst fades, the merged system stabilizes into a calmer, more mature form, often transitioning toward an elliptical galaxy with fewer new stars. Beyond their beauty, these star-forming events have deep significance for cosmic evolution. New stars produce heavy elements through fusion, and later scatter them into space through stellar winds and supernova explosions. These elements, carbon, oxygen, iron, and others, become the building blocks of future planets and life. Every element heavier than helium in your body, your bones, and your blood was once forged in a star and redistributed by events like these. Galactic collisions, by driving cycles of birth and death, are among the universe's most effective engines for creating complexity. Astronomers also study the efficiency of star formation in these environments. By comparing the amount of gas available to the number of new stars formed, scientists can determine how effectively collisions convert matter into light. Some galaxies convert gas into stars with remarkable speed, while others remain inefficient despite strong interactions. These variations help refine models of galactic evolution and the role of feedback processes such as radiation pressure, magnetic fields, and turbulence. From a distance, the process is silent. There are no sounds in space, only light, yet the physics behind this silence is immensely energetic. Each new star ignites as hydrogen fuses into helium, releasing enough energy to shine for billions of years. Multiply that by billions of stars, and a galactic collision becomes one of the brightest phenomena observable in the universe. Star formation during collisions shows that even in upheaval, the cosmos maintains balance. Where matter is compressed, creation follows. Where energy is released, structure stabilizes. It is a reminder that growth and destruction, light and gravity, work together in the same quiet equation that keeps the universe evolving. When we hear the phrase galaxies colliding, it's easy to picture stars smashing together like sparks from a grinding wheel. The reality is far more serene. In most collisions, not a single star directly hits another. The space between stars is so enormous that even as galaxies pass through one another, each sun continues on its path almost undisturbed. The true effects of a galactic collision are not violent impacts but slow shifts in motion, energy, and position. To understand why, it helps to grasp the scale of emptiness in a galaxy. If the sun were the size of a marble, the nearest star, Proxima Centauri, would be another marble roughly 700 kilometers away. The Milky Way is mostly space, thinly populated by stars scattered across distances so vast that even during a merger, most of them pass cleanly by. Yet despite this physical separation, the combined gravitational influence of billions of stars acts collectively, reshaping entire galaxies without a single stellar collision. This collective pull changes stellar orbits in subtle but lasting ways. As two galaxies interpenetrate, stars feel new gravitational gradients. Some are deflected outward into extended halos or tidal tails, while others are drawn inward toward the densest regions of the merging system. The orbits of stars can lengthen, tilt, or even reverse direction depending on the interaction's geometry. Astronomers can trace these changes long after the merger is complete, using stellar motion to reconstruct the event that caused it. Each star becomes a data point in the memory of the galaxy. Even though stars themselves rarely collide, the regions around them are affected. Clouds of gas that once surrounded these stars are stretched or compressed, changing how future generations of stars will form. Dense star clusters can be torn apart or scattered into new arrangements. The stability of planetary systems, too, may shift slightly, not through direct impact but through the gentle tug of altered gravity. For planets orbiting far from their suns, the change can be enough to modify climates or trajectories, though on Earth's timescale, such effects would unfold over spans longer than the age of our species. Astronomers simulate these interactions with remarkable precision. Supercomputer models follow the paths of millions of stars through gravitational equations, showing how entire galaxies evolve. In these simulations, the stars flow like grains of light through invisible currents, each moving smoothly according to Newton's and Einstein's laws. The results show that, despite the complexity of a collision, the outcome remains predictable. Gravity ensures that the chaos we imagine resolves into order. Over time, random motion settles into a new equilibrium, a single, stable galaxy where stars orbit peacefully once again. This long-term stability is a defining feature of the universe. While energy moves and matter shifts, the governing rules remain constant. After a collision, once the violent motion of gas subsides, the merged galaxy enters a calm phase. Star formation slows, orbits align, and dust clouds thin. What was once a turbulent scene becomes a vast, silent city of stars, each one shining quietly for millions or billions of years. To look at such a galaxy through a telescope is to witness the final stage of a process that began long before Earth even formed, a reminder that change does not always mean destruction. Some of the most beautiful galaxies in the sky, such as elliptical systems with smooth, glowing profiles, are the descendants of these collisions. Their calm appearance hides an energetic past, now forgotten in the regular motion of stars. The universe seems peaceful, but every point of stillness comes from movement that has already played out. Astronomers sometimes call this cosmic relaxation, the gradual settling of a system after an event. From a distance, galaxies appear frozen in time, their light reaching us after journeys of millions of years. But that light carries history. It tells of motion, pressure, heat, and balance, the universe finding calm after change. The stars themselves are evidence that order follows disruption, that the cosmos, though dynamic, always returns to harmony. So when we speak of colliding galaxies, it is worth remembering that even amid these vast encounters, tranquility persists. The stars do not crash, they adjust. They continue their long orbits through an ever-changing gravitational landscape. In that quiet persistence lies the true rhythm of the universe, patient, balanced, and unending. When two galaxies finally lose their separate identities, a slow merging begins that will reshape them into a single, larger system. This process unfolds over billions of years, yet its logic is simple. Gravity collects what was once scattered and distributes energy until balance is restored. What we call a collision is, in truth, a long negotiation between matter and motion that ends in stability. As the galaxies interlock, their centers drift toward each other. Each orbiting star continues along a new path, determined by the combined mass of both systems. Gas clouds swirl and twist, drawn into the deepening gravitational well at the core. There, the material heats, glows, and sometimes fuels bursts of star formation before settling into broader, smoother orbits. Over time, the distinct spiral patterns blur. The graceful arms that once defined each galaxy dissolve into an extended envelope of stars. In their place emerges a single structure, rounder, denser, and calmer. Astronomers call this stage a merger remnant. Its appearance depends on the orientation, size, and mass of the original galaxies. When two roughly equal spirals merge, the end product is often an elliptical galaxy. Stars in such systems move in random directions, giving them a soft, featureless look. Smaller collisions where a large galaxy absorbs a dwarf produce subtler results, faint shells, ripples, or star streams marking the trace of the smaller companion's former orbit. These patterns gradually fade as the system relaxes, leaving behind only the faintest memory of the event in the motions of its stars. In simulations, the physics of this transformation is clear. As the galaxies coalesce, dynamical friction, the drag created by gravitational interactions, slows their motion. Energy is transferred from large-scale orbital movement into the internal motions of stars and gas. That conversion of energy allows the galaxies to sink together, spiraling inward until their centers finally merge. The overall process conserves momentum while dispersing energy, ensuring that the new galaxy reaches equilibrium rather than flying apart. Supermassive black holes at the centers of the merging galaxies also drift inward during this stage. They form a binary pair that gradually loses orbital energy through interactions with surrounding matter. Eventually, they will coalesce into a single black hole, sending out a burst of gravitational waves. Though this final merger releases enormous energy, the distance between us and such events makes them gentle to observe, detected not through light, but through faint ripples in the fabric of space-time itself. The gas within the merging galaxies often responds last. Shock waves propagate through the interstellar medium, compressing some regions while dispersing others. This chaotic rearrangement can briefly reignite star formation before the supply of cold gas runs thin. Once that fuel is consumed, the new galaxy enters a quieter era. Its color shifts from blue, dominated by young stars, to yellow or red as older stars take over the light. The visual transformation marks a physical one, the end of a turbulent youth and the beginning of long, steady maturity. From Earth, astronomers can observe mergers in various stages across the sky. Some show two bright cores still distinct. Others, like NGC 7252, have already formed a single nucleus, surrounded by loops of stars, the remnants of earlier orbits. These snapshots allow scientists to assemble a continuous picture of evolution: approach, encounter, merger, and calm. Each system we see at a different stage is a chapter in that same universal pattern of rebirth. What emerges from this process is not ruin but renewal. The new galaxy holds within it the stars, gas, and dust of its predecessors, rearranged into a fresh design. Elements forged in earlier generations of stars become part of new ones. The cycle of creation and transformation continues without interruption. In this sense, every collision contributes to the universe's long habit of recycling, matter becoming structure, structure becoming matter again. To imagine this transformation is to witness the universe maintaining balance through change. Galaxies collide, merge, and settle not as acts of destruction, but as stages in an unending rhythm. Out of two patterns comes one, out of motion comes rest, and from apparent chaos emerges order. The cosmos, it seems, always finds a way to turn movement into meaning. After two galaxies complete their long merger, what follows is a period of quiet readjustment. The forces that once drove motion and turbulence give way to equilibrium. The stars, gas, and dark matter settle into new orbits under the influence of a single, unified gravitational field. What was once a complex dance of two spirals or irregular forms now becomes one structure, stable, bright, and enduring. The violence that observers might imagine is long past. What remains is calm, balance, and the slow continuation of time. Astronomers describe this stage as relaxation. The term sounds gentle, but it refers to a precise process. Random motions of stars and clouds gradually even out differences in energy. Each orbit adjusts minutely until the system as a whole reaches statistical balance. The result is a galaxy that appears smooth and symmetrical, its stars distributed evenly through a luminous halo. Over hundreds of millions of years, gravitational disturbances fade, leaving behind a steady glow of order. During this time, the central black hole may still accrete leftover gas, shining briefly as an active galactic nucleus before quieting. As the surrounding gas dissipates, the galaxy's light becomes dominated by older stars, yellow and red giants burning at moderate temperatures. The earlier bursts of blue star formation fade into memory. Astronomers viewing such systems see maturity, a population of long-lived stars radiating steadily, with little remaining fuel for future creation. The merger, once a source of motion, now gives rise to stillness. In computer simulations, this phase is represented by the slow reduction of chaotic motion. The outer regions of the galaxy stretch and flex as energy redistributes, while the inner regions stabilize first. What was once a pair of spiraling disks has become a spheroid, held together by uniform gravity. Gas that hasn't yet turned into stars sinks toward the center, adding faint new light to the core. Over time, this flow stops. As the last dense clouds are consumed, the galaxy enters a long, tranquil epoch that may last for billions of years. For scientists, this stage offers insight into the final shape of matter in the universe. It shows that complexity tends towards simplicity, that systems built on motion eventually find rest. The energy of the collision is not lost, it is diffused into a vast network of orderly movement. Every star, every atom of gas, continues to orbit according to predictable laws. The chaos that once defined the meeting of galaxies has transformed into structure and symmetry. Astronomers studying elliptical galaxies see this pattern everywhere. Many of these luminous, rounded forms are ancient merger remnants. Their light is soft, evenly distributed, and stable. They contain the history of countless collisions reduced to balance. Observing them is like reading the final page of a cosmic story, where every previous chapter of movement has settled into coherence. If you haven't drifted off yet, the calm of this stage suggests, this is the moment to let go. Just as two galaxies merge and then rest, your own mind can allow its separate thoughts to join and quieten. The same laws that shape the universe also favor balance. Sleep is, in its own way, a kind of equilibrium, the body and mind aligning into stillness after a day of motion. You don't have to seek it. Like gravity finding center, rest comes naturally once movement slows. In that sense, galactic mergers mirror the cycles we experience on a much smaller scale. Activity followed by calm, change followed by recovery. The universe never stops evolving. Yet within that constant transformation are long intervals of quiet stability. These resting periods are not empty, they are necessary, allowing order to take hold before the next wave of creation begins. When we look at an old elliptical galaxy glowing faintly at the edge of space, we are seeing the same kind of rest, an enduring peace written in starlight. The galaxies have merged, the energy has dispersed, and gravity holds everything in gentle balance. What once was two has become one, and what was motion has become calm. In the endless unfolding of the cosmos, every journey ends, for a time, in quiet. At the heart of nearly every large galaxy lies a supermassive black hole, an object so dense that not even light can escape its gravity. These cosmic centers act as both anchors and engines. Though invisible, they shape the orbits of surrounding stars and control the flow of gas across vast distances. Understanding how they behave during and after galactic collisions has become one of modern astronomy's most revealing pursuits. A supermassive black hole can range from millions to billions of times the mass of the Sun. The one in the center of our Milky Way, known as Sagittarius A*, weighs about 4 million solar masses. Despite its enormity, it occupies a region smaller than the orbit of Mercury. Around it, stars move at tremendous speeds, tracing orbits that confirm its presence even though the object itself emits no light. What we see is the glow of gas as it spirals inward, heated by friction until it radiates in X-rays and radio waves. When galaxies merge, their central black holes are carried with them, drawn by the deepening gravitational field of the new system. As the merger progresses, the two black holes drift closer, each wrapped in a disk of hot gas. They form what astronomers call a binary black hole system. Over time, gravitational interactions with surrounding matter remove orbital energy from the pair, causing them to spiral slowly toward each other. Eventually, they merge into a single, larger black hole, releasing energy in the form of gravitational waves, ripples that propagate through space-time itself. These waves were first directly detected on Earth in the 21st century, confirming predictions made a century earlier by Einstein's theory of general relativity. Each detection is a faint tremor from a distant event, proof that collisions between compact objects, whether black holes or neutron stars, really do send vibrations across the cosmos. Though we cannot see the black holes themselves, we can hear their mergers through these distortions in space-time, recorded as tiny changes in laser interferometers like LIGO and Virgo. During galactic mergers, the activity surrounding central black holes can become extraordinarily bright. As gas and dust funnel inward under gravity, they form accretion disks, rotating rings of material heated to millions of degrees. Some of that energy escapes in jets of charged particles streaming away at near-light speed. These jets can extend far beyond the galaxy, visible in radio and X-ray light. When this happens, astronomers describe the galaxy as hosting an active galactic nucleus, or AGN. Despite the name, what we see is not the black hole itself, but the effects of matter falling toward it. The energy produced by active black holes plays a vital role in regulating galaxy evolution. Powerful jets and winds from the nucleus push gas outward, heating and dispersing it. This process, known as feedback, limits further star formation by reducing the available supply of cold gas. It's a self-correcting mechanism. As the galaxy grows more active, it also stabilizes itself. Without this feedback, galaxies might form too many stars too quickly, collapsing under their own gravity. With it, they maintain balance, evolving slowly over billions of years. Observations across the electromagnetic spectrum have revealed the diversity of these galactic cores. Some black holes remain quiet, surrounded by little gas. Others blaze so brightly they can outshine their host galaxies. The most luminous examples are called quasars. Light from quasars has traveled billions of light-years to reach us, allowing astronomers to look back in time and witness how black holes shaped the early universe. Even in their violence, they serve a purpose, redistributing matter, energy, and momentum across cosmic scales. After a merger settles, the new central black hole becomes the gravitational anchor of the resulting galaxy. Around it, stars continue their orbits, gas flows, stabilizes, and the system regains equilibrium. The black hole itself grows only slightly larger but gains renewed influence over its surroundings. It is both a remnant of the past and a regulator of the future, a symbol of how the universe conserves and repurposes everything it creates. From a distance, none of this turmoil is visible. The galaxy appears calm, a smooth oval of light. Yet deep within its center lies an engine of immense gravity, an object that bends both space and time. Every star in that galaxy, every atom of dust, orbits in quiet obedience to it. Black holes remind us that the universe's greatest power often hides behind stillness, shaping everything without ever revealing itself. When two galaxies merge, their central black holes inevitably move toward each other, locked in a gravitational partnership that will end in one of the most powerful events in the universe. These collisions are invisible in ordinary light, yet they send out waves through the very fabric of space-time. Understanding how black holes meet, merge, and announce their union has opened a new chapter in astronomy, one that listens rather than looks. At first, the two black holes orbit each other at great distances, surrounded by dense fields of stars and gas. Each pass through this environment robs the pair of energy. Stars that wander too close are slingshotted away, carrying off momentum and gradually shrinking the orbit. The same happens with gas clouds. Friction and gravitational drag convert orbital motion into heat and radiation. This process is known as dynamical friction, and though it is invisible, it slowly tightens the black hole's embrace. Over millions of years, the distance between them decreases from thousands of light-years to mere light minutes. As they draw closer, the black holes form a binary system, circling each other with increasing speed. The gravitational energy released is extraordinary. Each orbit distorts space-time, creating ripples known as gravitational waves. These waves spread outward at the speed of light, stretching and compressing the geometry of the universe itself. When they finally reach Earth, they are unimaginably faint, changing the length of a 4-kilometer laser interferometer arm by less than the width of a proton, yet detectable thanks to instruments like LIGO, Virgo, and CAGRA. Each signal represents the final seconds of a merger that may have occurred billions of years ago. As the orbit tightens, the frequency of these waves rises, producing a characteristic chirp that scientists can convert into sound. By studying these waveforms, astronomers can measure the masses, distances, and spins of the merging black holes. It is a new kind of observation, a form of gravitational wave astronomy that complements traditional telescopes. Where light reveals structure, gravitational waves reveal motion and energy. Together, they provide a complete picture of how gravity behaves under the most extreme conditions. When the two black holes finally merge, they form a single, larger one. The event releases an enormous amount of energy, often more than is radiated by all the stars in the observable universe during that instant. Yet because the energy leaves as gravitational waves rather than light, the moment passes silently in every electromagnetic sense. The newly formed black hole settles into a stable state, slightly distorted at first, then smoothing out as it emits the last ripples of energy. Astronomers call this phase the ringdown, named for its resemblance to the fading vibration of a struck bell. These mergers have consequences beyond the black holes themselves. The release of energy can heat and stir the surrounding gas, influencing future star formation in the host galaxy. The merged black hole may also receive a kick, a recoil velocity caused by asymmetry in the gravitational waves emitted. In rare cases, this can eject the black hole from the galaxy's center, sending it drifting through space as a lone, invisible traveler carrying the combined mass of two cosmic giants. Such wandering black holes are difficult to detect, but indirect evidence suggests they exist. The discovery of gravitational waves confirmed that the universe is not silent. Space-time itself can vibrate, and those vibrations carry information across billions of light-years. Each detection is a direct message from the depths of gravity's domain, an event too compact for light but perfect for waves. With every new signal, scientists refine their understanding of how galaxies evolve and how the invisible skeleton of gravity binds everything together. It is remarkable to think that human instruments, built on a small planet orbiting an ordinary star, can sense tremors from the collision of black holes, millions or billions of times the Sun's mass. These detections connect us to events that happened when galaxies were young, long before Earth existed. They remind us that physics is universal. The same equations governing a dropped stone describe the merger of black holes across cosmic distances. When black holes collide, they don't produce chaos but clarity, a demonstration of gravity's consistency and reach. The universe does not shout, it hums. In that hum, faint but steady, lies proof that space and time are not empty but alive with motion. From our position on a small planet orbiting an ordinary star, the idea of watching galaxies collide seems almost impossible. The scale is too vast, the timescales too long. Yet, with the right instruments, astronomers can observe these immense events in remarkable detail. Every image, spectrum, and radio signal we capture tells part of the story of how the universe builds and reshapes itself through collisions. Light is our first messenger. When telescopes collect light from distant galaxies, they are not recording the present but the past. Because light travels at a finite speed, even nearby galaxies appear as they were millions of years ago. The farther we look, the older the light becomes. In the case of galactic collisions, we are witnessing moments that began billions of years before humanity existed. Each image of two galaxies in contact is therefore a snapshot from a story still unfolding. Astronomers use a wide range of tools to study these interactions. Optical telescopes reveal the visible light of stars and gas, showing the broad shapes and distortions caused by gravity. Infrared telescopes penetrate dust to reveal regions where new stars are forming. Radio telescopes detect the faint signals of hydrogen gas, tracing how material moves between galaxies. And X-ray observatories capture emissions from hot gas near black holes or shock waves created during collisions. Together, these instruments form a multi-wavelength portrait of galactic evolution. The Hubble Space Telescope has been one of the most influential tools for this kind of observation. Its clear view above Earth's atmosphere has provided images of hundreds of interacting galaxies at various stages of collision. The clarity of these pictures allows astronomers to measure distances, brightness, and color, converting visual beauty into data. The James Webb Space Telescope, with its sensitive infrared eyes, now extends that reach deeper into dusty regions and farther into the past, revealing the earliest known mergers from when the universe was still young. Ground-based observatories add another dimension. The Atacama Large Millimeter Divided by Sub-Millimeter Array, ALMA in Chile, maps cold gas and dust in colliding galaxies, showing where new stars will form in the future. Spectroscopic instruments on telescopes like the Very Large Telescope, VLT, or Keck Observatory split light into its component wavelengths, revealing motion through Doppler shifts. Redshift tells astronomers how fast parts of a galaxy are moving away, while blue shift reveals those coming toward us. By combining this information, scientists can reconstruct three-dimensional motion from two-dimensional images. Observation alone, however, cannot capture billions of years of change. To fill in the gaps, astronomers turn to numerical simulations, computer models that use the laws of physics to recreate galactic encounters. These simulations can be paused, reversed, or accelerated to test different scenarios. When a simulated galaxy's shape matches an observed one, scientists can infer how long the interaction has been underway and predict what will happen next. In this way, simulations act as laboratories for understanding cosmic history. One of the most famous real examples is the antennae galaxies, located about 60 million light-years away. In visible light, they appear as two golden cores surrounded by long arcs of stars, the antennae that give them their name. Infrared and X-ray observations reveal regions of intense star formation and the heating of gas as the galaxies merge. By comparing these observations to simulations, astronomers have determined that the antennae are roughly halfway through their collision and will eventually form a single elliptical galaxy. Even with all our technology, these studies remain acts of patience. Collisions evolve so slowly that astronomers must rely on statistical sampling, comparing hundreds of galaxies at different stages to piece together a continuous timeline. It is like watching a tree grow by studying a forest of trees of different ages. Each provides a glimpse of a single phase in a process that no one observer can witness from beginning to end. Despite their vastness, these events connect directly to us. The light entering a telescope's mirror has crossed billions of kilometers, carrying the record of cosmic motion. When that light reaches a detector and becomes an image, it links human perception to the deepest processes of the universe. Observing collisions from Earth reminds us that knowledge itself is a form of participation, a way of being present in events far beyond our physical reach. To understand galactic collisions, we must first accept that they occur on timescales far beyond ordinary comprehension. The forces that move galaxies act continuously but slowly, their effects visible only when measured over millions or billions of years. What we call a single event is, in truth, a chain of processes unfolding across epochs so long that even entire species could rise and vanish before any visible change occurs. Astronomers often use light years and parsecs to describe distance, but when it comes to time, their language shifts to millions and billions of years. The motions that guide galaxies are governed by gravity, which acts instantly but alters motion gradually when masses are separated by vast distances. For example, while planets orbit their stars in years, stars orbit the centers of galaxies in hundreds of millions of years, and galaxies orbit within clusters on even longer scales. A galactic collision, from first approach to final merger, can take 2 or 3 billion years, roughly a quarter of the age of the universe itself. To put this into perspective, imagine shrinking cosmic history into a single human lifetime. The universe would be born in infancy, with the first galaxies forming in its early years. Galactic collisions would play the role of slow, inevitable transformations, akin to continents drifting or mountains eroding. Even the most violent cosmic events happen at the pace of geological change, multiplied by 1,000. For astronomers, studying such processes requires both patience and ingenuity. The patience to accept that direct observation will never show the full sequence, and the ingenuity to reconstruct it from scattered evidence. Light itself carries the timeline. Because it travels at a finite speed, every photon that reaches us tells of a moment long gone. When we observe two galaxies in collision, we are looking back in time by tens or hundreds of millions of years. Some of the most distant mergers we detect today began when the universe was young, a reminder that we live surrounded by the past. The sky is a library of delayed messages, each beam of light a record of what once was. To visualize the pace of a galactic collision, Astronomers often create time-compressed simulations. These computer models condense billions of years into a few minutes, showing how galaxies approach, twist, and merge. The result is dramatic, but it hides an important truth. In reality, everything happens in silence and slow motion. Nothing explodes, nothing rushes. The cosmos moves according to precise, predictable equations. Matter follows curvature, and curvature follows mass. Gravity does not hurry, it only persists. For scientists, working with such immense timescales presents both challenge and wonder. They must use indirect measurements, the positions and motions of galaxies, the ages of their stars, the color of their light, to reconstruct how long each phase lasts. The color of a galaxy, for example, reveals the age of its stellar population. Blue light indicates youth, red suggests maturity. By comparing thousands of galaxies of different colors and shapes, astronomers can infer the sequence of transformation and estimate how long each stage endures. Time also leaves its mark in the chemical composition of galaxies. The abundance of heavy elements, called metallicity, increases as generations of stars live and die. When astronomers measure metallicity across galaxies, they are reading a timeline of creation and recycling that spans billions of years. Every atom of oxygen or iron in a galaxy's gas tells a story of previous stars, explosions, and mergers. The record is written not on paper but in the spectra of light. For us, human time feels linear and limited, measured in days and decades. Cosmic time is circular and patient. It flows at a pace that transforms everything while appearing motionless to the observer. Recognizing this difference changes perspective. It reminds us that stillness and movement are relative, that what seems unchanging is merely changing too slowly for us to notice. When astronomers say that the Milky Way and Andromeda will collide in about 4 billion years, they speak not of an impending disaster but of an inevitable phase in the universe's ongoing rhythm. On that timescale, even stars live brief lives. Galaxies endure, reshaping and renewing themselves across ages. Understanding cosmic timescales is not about learning numbers, but about grasping proportion. It teaches humility, that our lifetimes are small threads woven into a tapestry stretched across eternity. In that vast measure of time, the universe is never in a hurry. It simply continues, guided by rules that are patient, steady, and sure. Every galaxy, every cluster, and every cosmic structure we observe is shaped by something we cannot see. This unseen component, known as dark matter, outweighs all visible matter by roughly a factor of 5. Though invisible to telescopes, its gravity is unmistakable. It forms the framework on which galaxies build themselves, and it determines how they move, merge, and survive. Without dark matter, the universe as we know it could not exist. The idea of dark matter emerged from careful observation rather than theory. In the early 20th century, astronomers noticed that galaxies in clusters moved faster than their visible mass could account for. Later, measurements of how stars orbit within galaxies revealed the same pattern. The outer stars moved at almost the same speed as those near the center. If gravity came only from the visible stars and gas, those outer stars should have drifted away into space. Something unseen was providing the extra pull, keeping everything bound. That invisible mass, spread in a vast halo around each galaxy, became known as dark matter. It does not emit, absorb, or reflect light. Its presence is known only through its gravitational effects. Today, astronomers detect it by measuring how it bends light from distant objects, a phenomenon called gravitational lensing. When light passes through a region containing a concentration of dark matter, it curves slightly, distorting the shapes of background galaxies. By analyzing these distortions, scientists can map the distribution of dark matter, creating a picture of the universe's hidden structure. Dark matter behaves differently from ordinary matter. It does not collide or clump in the same way that gas and dust do. Instead, it forms large, smooth halos extending far beyond the visible edges of galaxies. These halos act like invisible scaffolding, their gravity providing stability to the systems within. In simulations, Galaxies form first in regions where dark matter density is high. Gas falls into these gravitational wells, cools, and condenses to form stars. In this way, dark matter defines the very architecture of the universe, not by shining, but by shaping. When galaxies collide, it is their dark matter halos that meet first. Long before the luminous parts touch, the halos begin to merge, creating a deeper gravitational field that draws the visible galaxies together. The halos absorb much of the kinetic energy of the collision, allowing stars and gas to settle into new orbits without being flung into intergalactic space. This hidden interaction is what makes galactic mergers graceful rather than catastrophic. Dark matter cushions the process, smoothing the transition from two galaxies into one. Large-scale computer simulations of the universe, such as the Illustris and Millennium projects, show this vividly. When scientists model the cosmos including only visible matter, galaxies fail to form correctly. Add dark matter, and the universe suddenly looks familiar. Filaments of galaxies connect across vast distances, clusters form at intersections, and voids stretch between them. These structures match the patterns astronomers observe through deep sky surveys. The conclusion is unavoidable. Dark matter is the invisible skeleton of the cosmos, the hidden geometry that dictates where everything else will go. Despite decades of study, the true nature of dark matter remains one of science's most compelling mysteries. It may consist of undiscovered particles, perhaps interacting only through gravity and the weak nuclear force. Experiments deep underground and in space are searching for signs of these particles, hoping to catch even a single trace. So far, all evidence comes from gravitational effects, yet those effects are so consistent that few doubt dark matter's existence. The role of dark matter extends beyond structure. It influences the rhythm of cosmic evolution. By determining how galaxies cluster and merge, it shapes the long-term fate of the universe. It also provides an explanation for why galaxies survive collisions intact rather than dispersing into fragments. Dark matter's gravitational glue ensures that matter remains organized, guiding even the most violent interactions towards stability. Thinking about dark matter offers a kind of humility. It reminds us that most of the universe operates beyond direct perception. What we see, stars, planets, nebulae, represents only a small fraction of what is truly there. The rest, though unseen, is just as real, silently shaping everything from the smallest orbit to the largest cluster. In every galactic image, beneath the visible light, lies this invisible foundation. Dark matter does not need to shine to define reality. Its influence, constant and patient, holds galaxies together as they move, collide, and merge, ensuring that the grand design of the universe remains coherent and whole. Across the cosmos, patterns repeat. Matter moves, gathers, disperses, and then gathers again. The universe has no single heartbeat, yet it follows a rhythm, one defined by gravity, expansion, and time. Galaxies collide and merge, stars are born, live, and fade. The scale is so vast that it seems detached from daily life, yet the same balance that governs the heavens also exists within us. The universe is rhythmic, not because it intends to be, but because physics is orderly, and order creates patterns that feel like breath. Astronomers study these cycles through the movement of light and the structure of matter. Everywhere they look, they find motion and stillness working together. Stars orbit quietly around galactic centers. Gas clouds drift until gravity compresses them into suns. Even black holes, symbols of finality, participate in this balance by regulating how galaxies grow. From the largest clusters to the smallest atoms, everything in the universe follows the same rule. Change happens, then settles, then begins again. This cosmic rhythm isn't chaotic, it's remarkably stable. The universe expands, but gravity holds local systems together. Within galaxies, stars are born from collapsing gas clouds, fuse elements in their cores, and then return that material to space when they die. Those elements become part of new stars and planets. On longer scales, galaxies themselves undergo the same process, forming, merging, stabilizing, and forming again. It's a cycle of transformation without waste, where even destruction serves creation. When galaxies collide, the process may seem violent, but it obeys this same rhythm. After the disruption comes rest, after turbulence comes balance. Over billions of years, the two systems that once spun separately become one, their energies redistributed and their paths aligned. The universe does not rush, it flows. This steady unfolding is what makes it both eternal and calm. Motion within peace, change within order. Astronomers have learned to recognize these rhythms through observation. Variations in starlight reveal pulsating stars, whose brightness rises and falls in perfect cycles. The motion of galaxies in clusters shows oscillations caused by gravitational tides. Even the faint background radiation of the cosmos, the afterglow of its birth, contains ripples that record the first beats of this universal pattern. Each layer of observation, from light waves to galactic motion, fits into the same quiet design. Human beings live too briefly to perceive these rhythms directly, but we are made of their outcomes. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all were forged in ancient stars that followed this same cosmic pulse. To understand that connection is to see ourselves not as observers, but as participants in a vast, ongoing equilibrium. The laws that guide galaxies also guide the chemistry of our cells. We move through life inside a universe that never stops breathing. If you're still awake, this thought might whisper, you don't need to follow the pace of the day anymore. The cosmos moves slowly, and it welcomes rest. Just as galaxies drift into balance after long motion, the mind, too, can settle after its own collisions of thought. There is no hurry to sleep. It comes naturally when stillness replaces striving. The same forces that align galaxies work silently within you, turning motion into calm. As astronomers trace this grand rhythm, they see not randomness but grace. Each merger, explosion, and collapse is part of a continuous flow toward order. The stars that vanish return their matter to the next generation. Galaxies that collide create new ones in their place. The cosmos is patient with itself, and that patience is its greatest harmony. When you imagine galaxies moving through space, picture them not as separate events but as notes in a vast composition. The rhythm they follow is the same that governs the tides, the breath, the seasons, and the slowing of thought before sleep. In that rhythm lies both creation and rest, proof that the universe, in all its immensity, has never truly been chaotic. It has simply been unfolding, one calm cycle at a time. After the merging of galaxies, the universe does not pause. The remnants of these collisions become fertile ground for new beginnings. Vast clouds of gas and dust, once scattered, now concentrated, cool, condense, and begin forming new generations of stars. Around these newborn stars, disks of material give rise to planets, moons, and asteroids. From the apparent chaos of collision emerges creation on every scale. This cycle of renewal is one of the defining patterns of the cosmos. When two galaxies interact, their gas clouds compress under tidal forces and shocks. In those compressed regions, gravity overcomes pressure, and the gas begins to collapse inward. The collapse continues until temperature and density become high enough to ignite nuclear fusion, the process that turns hydrogen into helium and releases light. Every star that shines is a direct result of that balance between pressure and gravity. Star formation occurs in clusters, not isolation. A single collapsing cloud can produce hundreds or thousands of stars. The most massive among them burn their fuel quickly, often lasting only a few million years before ending in supernova explosions. These explosions scatter heavy elements, carbon, oxygen, silicon, iron, back into space. That material enriches the surrounding gas, seeding it for future generations of stars and planets. The smaller, longer-lived stars remain for billions of years, glowing steadily in the merged galaxy's arms or core. Around many young stars, leftover dust and gas flatten into protoplanetary disks. Within these disks, particles collide and stick together, forming clumps that grow into planetesimals and eventually planets. The physics is simple but slow. Dust becomes rock, rock becomes worlds. The variety of planets that can emerge, gas giants, rocky Earth-like bodies, icy moons, depends on temperature, composition, and distance from the parent star. The same basic processes that once shaped our own solar system occur wherever gas and gravity cooperate. Astronomers have witnessed these early stages through instruments like the James Webb Space Telescope, which can peer into dusty star-forming regions invisible in ordinary light. Images of nebulae such as the Carina and Orion show columns and filaments where new stars are still being born. In many of these nurseries, disks of material around young stars are already visible, glowing in infrared light as they spin. These glimpses confirm that planetary formation is not rare but routine, a natural outcome of how galaxies evolve after collisions. Over time, as the new galaxy stabilizes, star formation slows. Gas is used up or heated by feedback from massive stars and black holes, preventing further collapse. The galaxy settles into equilibrium. Older stars dominate its light, while clusters of younger ones mark the places where creation recently occurred. This balance between activity and rest defines the long-term life cycle of galaxies. Even though we measure these events in billions of years, they represent the most creative phases of cosmic history. Every new star that forms adds light to the universe. Every new planet that condenses adds complexity, a potential site for atmosphere, chemistry, and perhaps life. The building blocks of living systems are distributed during these starburst epochs, carried by dust grains across interstellar space. In this way, galactic collisions do more than rearrange matter, they spread the ingredients for future worlds. Our own solar system likely owes its existence to a long chain of such events. The atoms in our bodies were forged in stars that lived and died before the sun was born. Those atoms drifted through space until they gathered again in the nebula that formed our solar system. In that sense, we are descendants not only of stars, but of galaxies that collided and renewed themselves countless times before our world existed. The birth of new stars and planets after galactic collisions is the universe's way of ensuring continuity. What appears as destruction from a distance is, in truth, part of an unbroken cycle of creation. Stars die so that others may form. Galaxies merge so that new structures can emerge. Through this constant transformation, the cosmos preserves its balance, energy and matter never wasted, always reimagined. When we look at distant nebulae glowing softly in the night sky, we are seeing this process mid-act: matter gathering, gravity shaping, and light being born. The universe, though vast and ancient, is still creating. It is still building places where light can shine and where, perhaps one day, consciousness can wonder at the stars that gave it life. Galaxies are not static structures. Their forms evolve over billions of years, shaped by gravity, rotation, and the slow exchange of matter and energy. What begins as a loose cloud of gas and dark matter becomes, through time, a coherent design, sometimes a spiral, sometimes a sphere, sometimes something between. Each shape represents both a moment in time and a record of its history, the visible handwriting of gravity across the fabric of the universe. Astronomers classify galaxies by their appearance, but those appearances are snapshots in a long process of transformation. A young galaxy often begins as an irregular mass of gas and stars. Over time, its rotation flattens it into a disk, and spiral arms emerge where density waves trigger new star formation. These arms act like traffic jams in the flow of gas and stars, regions where material piles up, brightening temporarily before drifting onward. The result is the elegant spiral structure familiar from images of the Milky Way or Andromeda. When galaxies collide, their shapes change dramatically. Spiral arms stretch and twist, cores distort, and long tidal tails form as stars are drawn outward. If the collision involves galaxies of similar mass, the ordered motion that creates spirals is disrupted. The star's orbits become random, and the merged system settles into an elliptical galaxy, a round, smooth shape with little internal structure. In smaller collisions, where one galaxy dominates, the larger often remains roughly spiral, while the smaller is absorbed and stretched into faint streams of light. These structures, visible in deep images, serve as fossil evidence of past mergers. Over even longer timescales, elliptical galaxies may themselves merge into still larger forms, creating giant ellipticals found at the centers of galaxy clusters. These giants contain trillions of stars and are often surrounded by halos of diffuse light. Their smooth appearance belies a turbulent past filled with countless mergers. Astronomers studying their light spectra can estimate how many generations of stars have lived and died within them, revealing the story of accumulation written in color and brightness. Not all galaxies evolve through collisions alone. Some are sculpted by their environment. Galaxies near the dense centers of clusters experience ram pressure stripping, where gas is pulled away by the hot plasma that fills the space between galaxies. Without gas, they can no longer form new stars, fading into red, quiescent systems. Others are stretched by the collective gravity of neighbors, creating warped disks or elongated shapes. In the quiet outskirts of clusters, galaxies evolve more gently, preserving spiral structures for much longer. Dark matter halos play an invisible but decisive role in this evolution. The shape and density of a galaxy's halo determine how strongly it resists deformation. A dense halo can preserve structure even through moderate collisions, while a lighter one allows distortion. In this way, the unseen architecture of dark matter silently guides how galaxies look and behave. Simulations that include both visible and dark matter reproduce the full range of observed shapes, confirming that what we see in light mirrors what exists in shadow. The evolution of galactic shapes is also a story of energy balance. As systems merge, kinetic energy converts into heat, altering how stars and gas distribute themselves. Feedback from supernovae and black holes redistributes matter, clearing or compressing gas in different regions. Each cycle of energy exchange leaves subtle marks, a puff of dust here, a halo of hot gas there, until the system reaches a new equilibrium. The resulting galaxy may look tranquil, but its form encodes billions of years of dynamical activity. Observations from modern surveys, such as the Sloan Digital Sky Survey and the Hubble Ultra Deep Field, have provided statistical proof of this slow transformation. By comparing galaxies at various distances, and therefore different eras, astronomers can see how the population changes with time. In the early universe, irregular galaxies dominate. Later, spirals and ellipticals become more common. The shift marks the long transition from formation to maturity, from chaos to structure. When we look at the night sky, each faint smudge of light represents not a single moment, but an entire evolution. Its shape, color, and brightness tell us where it stands in its life cycle. The elegant spirals we see today will one day fade into smooth ellipticals. The ellipticals themselves may merge into something larger still. In the universe, nothing remains fixed. Everything changes form, yet nothing is truly lost. The shapes of galaxies, like the shapes of clouds, are temporary expressions of underlying motion, a reminder that beauty in the cosmos is always in transition. Galaxies rarely travel through the universe alone. Most belong to clusters, enormous assemblies containing hundreds or even thousands of galaxies bound together by gravity. These are the largest gravitationally stable structures known. Inside them, galaxies move through a common sea of hot gas and dark matter, interacting, colliding, and slowly reshaping one another. Understanding clusters helps scientists see not just individual galaxies but the architecture of the cosmos itself. A typical cluster spans several million light-years. Its total mass can reach a quadrillion times that of the Sun, yet only a small fraction of that mass comes from visible stars. About 15% is gas heated to tens of millions of degrees, glowing in X-rays. The remaining majority, more than 80%, is dark matter, forming an invisible skeleton that holds the cluster together. This combination of light, gas, and shadow gives clusters their unique stability and complexity. Within a cluster, galaxies move at high speeds, often 1,000 kilometers per second or more. These motions are governed by the collective gravity of the entire system. When two galaxies approach each other inside this crowded environment, the surrounding gas and the cluster's gravitational tides influence how the encounter unfolds. Collisions here are frequent compared with the quieter outskirts of the universe. Many galaxies near cluster centers have already merged multiple times, their once spiral shapes transformed into smooth ellipticals. Clusters are therefore both cradles and graveyards of galactic evolution. One of the defining features of clusters is the intra-cluster medium. the vast reservoir of thin, superheated gas that fills the space between galaxies. Though almost empty by earthly standards, this plasma contains more mass than all the galaxies combined. It emits X-rays that telescopes such as Chandra and XMM Newton can detect, allowing astronomers to map its temperature and density. These observations reveal shock waves and ripples created by past mergers, as well as cavities blown by jets from active black holes in the cluster's central galaxy. The intracluster medium acts as both record and regulator of a cluster's history. Clusters themselves form through mergers, just as galaxies do. Smaller groups fall together under mutual gravity, combining into ever larger structures. When two clusters collide, the event releases unimaginable energy. Yet even at that scale, motion remains graceful and slow, gas clouds flowing around one another, dark matter halos overlapping, and shock fronts spreading gently through space. The bullet cluster is one of the most studied examples. It shows how visible matter and dark matter separate during impact, offering direct evidence that dark matter interacts primarily through gravity, not through friction or light. Astronomers use clusters as cosmic laboratories for testing theories of physics. Because they contain so much mass, they bend light from objects behind them through gravitational lensing, magnifying distant galaxies. By studying these distortions, scientists can map dark matter distribution and measure the total mass of the cluster with precision. The results consistently show more mass than visible matter alone could supply, one of the strongest confirmations of dark matter's dominance in the universe. Clusters also play a crucial role in cosmic expansion studies. Their number and distribution at different distances help determine how quickly the universe has grown over time. Observing clusters across cosmic history allows astronomers to test models of dark energy, the mysterious force driving accelerated expansion. In this way, clusters serve as measuring sticks for both matter and time, linking the behavior of galaxies to the fate of the cosmos. Life within a cluster is harsh for galaxies. The hot plasma strips away their outer gas in a process called ram pressure stripping, depriving them of the raw material for new stars. As a result, most central cluster galaxies are red and old, their star formation long ended. Yet, this same process enriches the intracluster medium with heavy elements, distributing the products of stellar evolution across millions of light years. Even in apparent decline, clusters recycle material, ensuring that nothing is truly lost. Viewed from afar, a galaxy cluster resembles a glowing web suspended in darkness. Bright knots where galaxies congregate, filaments of gas between them, and a faint halo of X-ray light enclosing all. It is a structure of immense scale but delicate balance, where gravity and energy exchange maintain order over billions of years. Clusters remind us that the universe is not empty but intricately connected, a network of matter, light, and invisible force stretching beyond imagination. If we could step far enough away from the universe to see it in its entirety, we would not find galaxies scattered randomly through space. Instead, we would see a structure of remarkable order, a vast, three-dimensional network of filaments and nodes linking galaxies, clusters, and dark matter halos together. Astronomers call this grand structure the cosmic web. It is the largest pattern ever observed, extending for billions of light years and giving the universe its cellular, almost organic appearance. The cosmic web formed from small irregularities that appeared shortly after the universe began to cool. Slight differences in density, tiny ripples in the early distribution of matter served as seeds for all later structure. Over time, gravity amplified those ripples. Denser regions pulled in more material, while emptier regions lost it. What began as faint variations in the young universe grew into a network of filaments where matter gathered, leaving enormous voids between them. This process, driven by dark matter, continues even now, shaping how galaxies cluster and evolve. Modern simulations of the universe reproduce this structure in striking detail. Programs such as Illustrious TNG and Millennium begin with known physics, gravity, hydrodynamics, and cosmic expansion, and evolve billions of particles over cosmic time. The resulting images reveal a filamentary pattern matching what astronomers see through deep sky surveys, long strands of matter converging at luminous intersections where galaxy clusters reside. Between these filaments lie the great cosmic voids, immense regions almost empty of galaxies but not of matter. They contain thin traces of gas and dark matter, enough to keep the web connected. The filaments themselves act like highways of cosmic material. Gas and galaxies move along them under gravity, feeding clusters at the intersections. These flows deliver the raw ingredients for new stars and black hole growth. In this way, the cosmic web is not a static pattern but a dynamic circulation system. Galaxies are both passengers and builders within it, formed by its structure and simultaneously strengthening it through their own gravity. Astronomers map the cosmic web using several complementary techniques. Optical and infrared surveys, such as the Sloan Digital Sky Survey, record the positions and redshifts of millions of galaxies, turning data points into a three-dimensional picture of large-scale structure. Radio telescopes trace the faint signal of neutral hydrogen that threads between galaxies. More recently, instruments observing the Lyman alpha forest absorption lines in the spectra of distant quasars have revealed filaments of gas stretching across otherwise dark space. Each observation confirms that matter is not evenly spread but woven into an intricate cosmic lattice. The cosmic web also acts as a laboratory for cosmology. Its pattern encodes information about the amount of dark matter and dark energy in the universe. The spacing of filaments and the size of voids depend on how fast the universe expands and how gravity operates over large distances. By comparing observations with simulations, scientists refine measurements of these fundamental quantities. The web, in this sense, is a cosmic archive containing the story of everything that has ever existed. Even though its scale defies imagination, the geometry of the web follows simple mathematical principles. Regions of high density grow faster, while low-density voids expand more rapidly as gravity pulls matter away from them. Over billions of years, filaments stretch and thin, but their overall pattern remains. It is a self-similar structure. Zooming in or out reveals the same branching forms. This fractal-like quality is why astronomers often describe the cosmic web as the universe's skeleton, an underlying framework that supports everything we can see. From our small position inside one of its filaments, humanity glimpses only a fragment of this design. The Milky Way sits within a thread of galaxies known as the local sheet, which is part of the Laniakea supercluster, our local region of the web. Beyond it, countless other filaments connect clusters like strands of light on a vast invisible net. Each galaxy, no matter how isolated it appears, is linked to the rest through gravity and motion. To picture the cosmic web is to realize that the universe is not a void but a structure, delicate, continuous, and alive with motion. The same gravity that shapes galaxies also shapes the spaces between them, turning emptiness into form. On the grandest scales, the cosmos resembles a single, interconnected organism, breathing slowly through the exchange of matter and light along its filaments. We live inside that web, part of its pattern, held in place by threads we cannot see but that connect us to everything that ever was. The universe is not a fixed arena where galaxies drift through empty space. Space itself is stretching. This concept, cosmic expansion, is one of the most important discoveries in modern science. It reshaped our understanding of time, distance, and the fate of everything that exists. When we say galaxies move away from us, we are not describing motion through space, but motion with space. The very fabric of the cosmos grows larger, carrying galaxies along like dust suspended in rising dough. The first evidence of this expansion came from light. Astronomers noticed that distant galaxies emitted light shifted toward longer, redder wavelengths, an effect now known as redshift. The farther away a galaxy lies, the greater this redshift appears. This relationship, described by the Hubble-Lemaitre law, means that distance and recession speed increase together. Space is expanding uniformly in all directions. The universe has no center. Every observer, wherever they are, sees other galaxies receding. The discovery transformed our perception of the cosmos. Instead of a static, eternal framework, the universe became dynamic, born from a denser, hotter state, and still growing today. This expansion began roughly 14 billion years ago and continues at a measurable rate. Yet it is not the galaxies themselves expanding, but the scale of space between them. Within galaxies, gravity holds stars and planets together, resisting the stretch. Only the vast distances between clusters change meaningfully with time. To visualize expansion, astronomers often use analogies. One is a balloon covered in dots. As the balloon inflates, every dot moves away from every other dot, yet no single point marks the center. Another analogy is raisin bread rising in an oven. Each raisin stays the same size, but as the dough expands, the distances between raisins increase. These comparisons are imperfect but useful. They emphasize that galaxies are not flying through pre-existing space, but are part of an expanding medium. What drives this expansion is the most mysterious component of the cosmos: dark energy. Observations show that the universe's expansion is not slowing down, as gravity would predict it's accelerating. This means something is counteracting gravity on the largest scales, pushing space outward faster and faster. Scientists estimate that dark energy accounts for about 70% of the total energy content of the universe. Its nature remains unknown. It might be an intrinsic property of space itself, a cosmological constant that Einstein once introduced and later dismissed, or it could be something deeper, an evolving field still beyond measurement. To detect and measure this expansion, astronomers rely on precise observations. They study type Ia supernovae stellar explosions so consistent in brightness that they serve as cosmic distance markers. By comparing their apparent brightness with their redshift, scientists can calculate how the expansion rate has changed over time. Other tools, like the cosmic microwave background radiation, provide a snapshot of the early universe, revealing that expansion began with incredible speed and has been slowing and accelerating in different eras. Expansion affects everything from the way galaxies interact to how light travels across space. Over billions of years, the most distant galaxies will recede beyond the reach of observation. Their light, stretched endlessly by expansion, will fade until it can no longer reach us. The observable universe will grow darker, though the universe itself will continue expanding. This future, often called the cosmic horizon, defines the limit of what can ever be known or seen. Despite its vastness, expansion is a uniform, elegant process governed by simple physical laws. The same equations that describe a falling apple, Newton's laws of motion, and Einstein's general relativity also describe the stretching of the universe. The difference is only scale. The cosmos behaves like a single system, where every part influences the rest. Understanding expansion changes perspective. It reveals that even apparent stillness is movement, that every galaxy, every atom of intergalactic gas, and every photon of light participates in a slow, steady drift through time. The universe is growing, and with it, the distances between everything within it. Yet the fundamental connections remain. Gravity still binds stars, dark matter still shapes galaxies, and the web of energy and structure persists even as it stretches. The expansion of the universe is not just an astronomical fact, it is a reminder that change is woven into existence itself. Nothing remains fixed, not even space. What we call emptiness is alive with motion, carrying us all outward on an invisible tide that began long before Earth existed and will continue long after its last light fades. Every part of the universe is moving. Galaxies drift within clusters, stars orbit within galaxies, planets circle their suns, and even the smallest atoms vibrate with motion. Nothing is ever completely still. What seems calm is simply motion in balance, the quiet equilibrium that emerges when countless movements cancel one another out. To live in the universe is to live within a perpetual current, a continuous exchange of energy that never truly stops. Astronomers describe this movement with precision, but it can also be seen as rhythm, not poetic invention, but measurable fact. The Earth spins once every 24 hours, orbits the Sun once each year, and carries us around the center of the Milky Way roughly once every 200 million years. The Milky Way itself moves toward the Andromeda Galaxy, both falling toward their shared center of gravity. Above all of this, space itself stretches, carrying galaxies apart even as local gravity brings others together. Motion defines structure, and structure defines motion. From a human perspective, these scales are almost impossible to grasp. Yet, motion connects us to the same physics that shapes the stars. The atoms in our bodies vibrate with thermal energy, just as gas clouds vibrate before forming stars. The blood that flows, the air that moves through lungs, the ocean's tides, the drift of continents, all are variations of the same principle: energy in motion, guided by physical law. We exist as participants in the universe's dynamic balance, not separate from it. Astronomers have found ways to detect and measure almost every kind of motion. Light itself carries information about movement through Doppler shifts, where wavelengths stretch or compress depending on direction. Through this, scientists know whether a star is approaching or receding, how fast galaxies spin, and how rapidly the universe expands. From these measurements, a remarkable picture emerges, not of chaos, but of consistent order. The motions of celestial objects follow patterns so precise that we can predict eclipses, planetary alignments, and even the future collision of galaxies billions of years in advance. Within galaxies, motion is organized but intricate. Stars orbit in flattened disks, gas clouds spiral inward, and dark matter halos rotate subtly around them. These motions maintain the galaxy's shape, redistributing matter and energy in a slow, perpetual flow. Over time, this internal movement transforms the galaxy's appearance. Spirals tighten, arms stretch, and colors shift as old stars fade and new ones ignite. Even what seems fixed, a glowing band of starlight across the night sky, is alive with hidden motion. On the largest scales, motion becomes almost invisible because it unfolds so slowly. Two galaxies can take billions of years to pass through each other. Yet if we could accelerate time, we would see the cosmos as a grand choreography, galaxies swirling, merging, and flowing like luminous clouds in a vast ocean. The forces that drive this motion are simple. Gravity pulls, expansion pushes, and equilibrium emerges where the two meet. If you're still awake, this endless motion might seem like a paradox. How can a universe always in motion also feel so calm? The answer lies in balance. Just as your own breathing continues while your body rests, the universe's constant movement coexists with stillness. Galaxies glide silently, stars turn quietly, and time moves forward without haste. To sleep, too, is not to stop. It is to flow differently, to let energy continue while consciousness rests. The cosmos has no true stillness, only perfect continuity. As astronomers map the universe's motion, they see repetition and harmony where randomness might have been expected. The same patterns echo across scales. Electrons orbit nuclei as planets orbit stars, as stars orbit galactic centers. From the microscopic to the cosmic, movement organizes everything that exists. It is not noise but structure, not confusion but connection. The awareness of this motion can be soothing. It means the universe does not rush toward an end. It evolves in steady rhythm, carrying everything forward together. What appears still is simply moving too slowly to notice. Every rotation, orbit, and vibration is part of one continuous wave that links the smallest atom to the widest cluster. Even as you rest, that wave moves through you. You are part of the motion that keeps the universe alive, a fragment of its quiet, unstoppable flow. Every galactic collision we observe in the night sky is also a glimpse of our own distant future. The Milky Way and the Andromeda Galaxy, our nearest large neighbor, are on a slow, inevitable path toward one another. Although they are separated by more than 2 million light-years of space, their mutual gravity has already linked their destinies. In roughly 4 billion years, they will begin to merge, creating a single, larger galaxy, sometimes called Milkomeda. This coming event is not a disaster, but a continuation of the same process that has shaped galaxies since the dawn of time. The Andromeda Galaxy is similar to our own in size and mass, a vast spiral with hundreds of billions of stars. Both galaxies move through a shared cloud of dark matter that amplifies their gravitational attraction. Their approaching speeds several hundred kilometers per second may sound immense, but in cosmic terms, this is gentle. The merger will unfold over billions of years, each phase lasting longer than the entire history of human civilization. When they first touch, the outer halos of stars and gas will interact. Long tidal streams will form, stretching across intergalactic space like luminous ribbons. Stars will be displaced, but direct collisions will remain rare. The vast distances between them mean that almost every star will simply pass another without contact. The real drama will occur in the gas clouds between stars. As they compress, they will ignite new bursts of star formation, filling the merged galaxy with brilliant clusters of young blue stars. Simulations of the Milky Way-Andromeda merger show that both galaxies will lose their spiral structure. Their ordered rotations will twist and distort as gravity redistributes angular momentum. Over time, the two systems will settle into an elliptical shape, rounder, smoother, and calmer. The Sun, by then a much older star, will likely survive the encounter. Its orbit will change, carrying it farther from the center of the new galaxy, perhaps into a wide, stable path, where it will continue shining quietly for billions of years more. Astronomers have used advanced numerical models to reconstruct what the sky might look like during this future event. From Earth, or whatever replaces it, the view will be extraordinary. Over millions of years, Andromeda will grow brighter and larger in the night sky until it dominates the heavens. When the galaxies begin to overlap, the sky will fill with arcs of light, clusters, and glowing bridges of stars. Eventually, the two galactic cores will appear as twin centers of brightness before merging into one. Even though this spectacle will unfold over unimaginable timescales, each stage is predictable according to the laws of physics. The merged Milky galaxy will likely become part of a larger gravitational system that includes the Triangulum Galaxy and other members of our local group. Over time, all of these galaxies will drift together, forming a single massive elliptical galaxy surrounded by a halo of ancient stars. Beyond this local island of matter, the accelerating expansion of the universe will carry other clusters farther away until they disappear beyond the cosmic horizon. In that far future, the sky will contain fewer visible galaxies, but the merged one will remain bright, a testament to gravity's enduring work. This vision of the future is not speculative fantasy but a projection based on measurable motion. Astronomers can trace the Andromeda Galaxy's approach through Doppler shifts in its light and through detailed modeling of the local group's dynamics. Everything follows the same laws that govern smaller motions: attraction, inertia, and energy conservation. The universe does not act randomly, it evolves with mathematical grace. The collision of the Milky Way and Andromeda will mark one of the last major transformations in our galactic neighborhood. It will complete a story that began billions of years ago, when both galaxies first formed from collapsing clouds of gas within the same region of space. Their union will not end the cosmos but simply usher it into another state of balance, one more chapter in the endless sequence of creation and renewal that defines the universe. When we look at the faint band of the Milky Way stretching across the sky tonight, we are seeing a structure both ancient and temporary. Its stars, its spiral arms, even its gentle glow are part of a pattern that will one day dissolve and reform. The sky will change, as it always has, but the laws guiding it will remain the same. The future of colliding galaxies, like their past, is written in the quiet, steady language of gravity. After galaxies merge and settle into new equilibrium, their stars continue to live out their life cycles. Each one, from the smallest red dwarf to the most massive blue giant, follows the same underlying rules of physics, fusion, balance, and eventual decline. But as cosmic time stretches forward, the rhythm of star formation slows. The universe that once blazed with countless newborn stars will grow quieter, dimmer, and older. The story of the cosmos will become one of endurance rather than creation. In the early universe, star formation was rapid and chaotic. Collisions between gas-rich galaxies triggered bursts of activity, producing dense clusters of short-lived, massive stars. Over time, as gas was consumed or expelled, those bursts faded. Today, the universe still creates stars, but at only a fraction of its former rate. In the far future, after the great mergers have stabilized, that rate will decline even more. the raw material for new stars' cold hydrogen will become scarce. What remains will reside mostly in isolated clouds, drifting too far apart to collapse easily under gravity. The long-term fate of stars depends on their mass. The most massive ones, those tens of times heavier than the Sun, burn fiercely and briefly, exhausting their fuel in just a few million years. They end in spectacular supernovae, scattering elements into space and leaving behind neutron stars or black holes. Medium-mass stars, like the Sun, have longer, steadier lives. They fuse hydrogen into helium for billions of years before swelling into red giants and shedding their outer layers, forming planetary nebulae with glowing shells of gas. What remains is a white dwarf, a dense, fading core that slowly cools over trillions of years. The smallest stars, red dwarfs, burn their fuel so efficiently that they can live for trillions of years. None of them have yet died. The universe itself is not old enough to see a single one reach its end. These faint stars will dominate the far future. Even when brighter suns have vanished, red dwarfs will continue to glow softly, keeping the universe illuminated by their steady light. Over unimaginable stretches of time, however, even they will fade into darkness, leaving behind cold remnants, black dwarfs scattered across space. By then, the merged galaxies will have changed shape again. Without active star formation to replenish their light, they will become diffuse and faint. Their stars will drift farther apart as gravity weakens and the universe expands. Some will be captured by black holes, others will wander alone between galaxies, yet even this gradual dispersal follows precise rules. Energy is conserved, and the orbits of stars evolve according to gravitational laws that remain unbroken across eternity. Black holes will become the dominant objects in the universe's later ages. The central black holes of galaxies, swollen by mergers and accretion, will anchor the remaining stellar systems. Over time, smaller black holes will merge with larger ones, releasing gravitational waves that ripple invisibly through space-time. These waves will carry energy away, allowing black holes to settle into stable configurations. Even though they represent regions from which nothing escapes, black holes themselves will eventually lose energy through Hawking radiation, a slow process that will take longer than all current cosmic history combined. The universe's distant future, sometimes called the degenerate era, will be quiet but not lifeless. The motions of stars, remnants, and dark matter will continue in slow, graceful patterns. Galaxies will dim, but gravity will still hold their remnants together. Even as light fades, the underlying geometry of the universe will persist, a silent framework connecting what remains. On these timescales, change becomes imperceptible, yet it continues as faithfully as ever. It is humbling to realize that everything familiar, the Sun, the Milky Way, the visible stars, represents a brief phase in a far larger continuum. The cosmos is not ending, it is evolving towards simplicity. Energy will still exist, gravity will still shape motion, and the remnants of stars will still orbit quietly through space. The universe's future will not be one of sudden darkness, but of slow transformation, brightness giving way to subtlety, motion slowing but never ceasing. Even in its dimmest epoch, the universe will remain orderly. The same laws that govern today's galaxies will still operate in the farthest future. The stars will fade, but their patterns, their orbits, and the space that contains them will continue their silent dance. The cosmos will never truly stop, it will simply rest in a slower rhythm, keeping its promise of continuity long after light itself has grown old. Black holes represent the most extreme form of gravity known in the universe. They are regions where matter collapses to such density that space and time themselves curve inward, allowing nothing, not even light, to escape. Though often imagined as cosmic destroyers, black holes are instead engines of order, transforming energy, matter, and motion into the clean geometry of space-time. As the universe ages and stars fade, they will become its last dominant structures, quietly governing the final flow of energy. Every large galaxy hosts a supermassive black hole at its center. These giants contain millions or billions of times the mass of the Sun and act as gravitational anchors, shaping the motions of stars and gas around them. During galactic collisions, the central black holes eventually merge, emitting enormous bursts of gravitational waves, ripples in the fabric of space-time that carry energy across the cosmos. Detectors like LIGO and Virgo have already recorded such signals from smaller black holes, confirming Einstein's prediction and revealing that even darkness can make the universe tremble. In the far future, when star formation ceases and luminous matter declines, these black holes will remain. Smaller ones will merge or be consumed by larger ones, simplifying the cosmic landscape. The resulting giants will sit at the centers of the remaining galaxies, surrounded by slowly orbiting remnants, white dwarfs, neutron stars, and fragments of planets. Over vast timescales, most of this material will either fall inward or drift away, leaving the black holes as the principal survivors of the visible universe. Yet even black holes are not eternal. According to quantum theory, they emit a faint form of radiation known as Hawking radiation, named after physicist Stephen Hawking, who first proposed it in the 1970s. This radiation arises from quantum effects near the event horizon, where pairs of particles form spontaneously. One particle falls in, while the other escapes, carrying energy away. Over incomprehensibly long periods, this process causes black holes to lose mass, shrink, and eventually evaporate entirely. For the largest black holes, this could take more than 100 quintillion years, a span so immense it renders the concept of time almost meaningless. When that evaporation occurs, the energy once trapped within will be released back into space as faint radiation. The universe, by then nearly empty of stars and matter, will be filled with a diffuse background of low-energy photons and particles. This will mark the end of structure as we know it. The grand patterns, galaxies, clusters, and filaments will dissolve into uniformity. Gravity will still exist, but it will have little left to shape. At that stage, the cosmos will enter what physicists call thermal equilibrium, a condition where all energy is evenly distributed and no further work can be done. It is sometimes described as the heat death of the universe, though the name is misleading. It will not be hot but cold, an expanse of faint radiation at near absolute zero, silent and stable. Entropy, the measure of disorder, will have reached its maximum. The universe will no longer change in any noticeable way. Yet even in this stillness, the laws of physics will continue to operate perfectly, as they always have. This distant epoch will be the universe's quietest phase. Space will be almost empty, filled only with ancient photons stretched by expansion to wavelengths so long they carry almost no energy. Black holes will have vanished, their mass converted to light. The cosmic web will be gone, replaced by uniform darkness. And still, the equations that describe gravity, quantum mechanics, and thermodynamics will remain valid expressions of balance that persist even when their stage has gone dark. Though it sounds like an ending, this future is better understood as a return to simplicity. The same energy that once built galaxies will continue to exist, merely spread thin across space. Nothing is lost, only transformed. The story of the universe is not one of decay but of change, from structure to smoothness, from brightness to calm. Every particle will still obey the same rules, every photon will still move at the same speed, and the cosmos, in its near silence, will still be complete. In this vision of the end, there is a strange peace. The universe began with energy too dense to comprehend and will end with energy too thin to detect, yet both states are governed by the same symmetry. It began as light, and it will end as light soft, even, endless. The universe, as we see it today, is vibrant with light and structure. Galaxies fill the darkness, stars burn with energy, matter flows along invisible filaments. Yet this liveliness represents only a temporary chapter in a much longer story. In the distant future, after galaxies have merged and stars have faded, the cosmos will become a quieter place. What remains will be vast, sparse, and nearly still, a realm where isolation replaces connection and light gives way to shadow. This stage, often called the Dark Era, will emerge gradually, not suddenly. The transformation begins when star formation stops. Without new stars to illuminate space, galaxies lose their brilliance one by one. The remaining light will come from long-lived red dwarfs, white dwarfs cooling slowly, and the faint glow of gas still heated by ancient collisions. As those sources fade, the night will deepen until only a few scattered points remain visible. Over trillions of years, even those lights will go out. The spaces between galaxies will widen as expansion continues. In our own region, the merged Milky galaxy will persist, but distant galaxies will recede beyond the cosmic horizon, their light stretched until it can no longer reach us. To future observers, if any could exist, the universe will appear smaller, enclosed, and almost empty. The great web of filaments and clusters will remain beyond visibility, not because it has vanished, but because the speed of expansion will carry it forever out of reach. On these unimaginable timescales, even communication becomes impossible. Light, which travels faster than anything else, will no longer be able to cross the growing gaps between isolated regions. Each surviving cluster or galaxy will become its own cosmic island, surrounded by unreachable darkness. Within each island, gravity will still bind the remaining stars and remnants together, but beyond that boundary, space will expand freely. The universe will become a mosaic of isolated pockets, each fading in solitude. The loneliness of this era is not emotional but physical, a condition defined by distance and silence. The particles that once danced together will drift apart. The photons that once connected them will lose their energy to the expanding void. Temperature will fall toward absolute zero. Entropy, the measure of energy's dispersal, will rise until no gradients remain, no contrasts of hot and cold, no sources or sinks of motion. The cosmos will approach equilibrium, not as an act of loss, but as the fulfillment of its own laws. Yet even in that apparent emptiness, patterns will persist. Gravity will still operate within local systems, shaping the slow orbits of black dwarfs and neutron stars. Occasionally, one of these ancient remnants may collide, releasing a brief flash of light, a final spark in a dark sky. But these moments will be rare, and the intervals between them will grow longer. Over time, the universe's rhythm will stretch into silence, its heartbeat slowed beyond measure. For scientists who study cosmology, this future is not cause for melancholy but for awe. The same equations that describe today's galaxies predict this distant stillness with exactness. It is the natural conclusion of a process that began with the Big Bang, energy expanding, cooling, and spreading evenly across space. The cosmos moves from concentration to balance, from chaos to simplicity. The end is not disorder, but perfect uniformity, a universe at rest. To imagine this future is to confront scale itself. The distances, durations, and transformations involved exceed anything the human mind was built to grasp. Yet, our ability to predict it demonstrates the power of reason and observation. From a small planet around an ordinary star, a species that has existed for only an instant of cosmic time has learned how the story continues long after it is gone. The future universe will be silent, but its silence will echo the order that made such understanding possible. When light finally fades and matter drifts beyond sight, the universe will not mourn its own quiet. It will simply continue, vast, cold, and complete. Energy will persist, the laws of physics will endure, and time itself will stretch onward without witness. The cosmos will have reached a state it has always been moving toward, perfect stillness in motion, a balance so stable it needs no observer to affirm it. When the universe eventually settles into darkness, the echoes of its dynamic past will still exist. Though galaxies may fade, the structure they created will leave enduring marks written into the geometry of space itself. Every collision, every merger, and every ripple of gravity has helped shape that hidden architecture. The universe's future may seem silent, but it carries the memory of everything that once was. The legacy of galactic collisions begins with their influence on structure. Each merger changed how matter was distributed, how dark matter halos overlapped, and how energy was exchanged between stars, gas, and gravity. Even after the visible components of galaxies fade, the curvature of space-time they sculpted remains. These distortions, minute but permanent, are like fingerprints in the cosmic fabric. They can never be erased, only stretched thinner as the universe expands. Gravitational waves, too, will continue to travel outward, carrying with them the imprints of every collision that ever occurred. Though their energy will weaken as space stretches, they will persist indefinitely, faint ripples crossing the endless dark. In the absence of light, these waves become the universe's final form of communication, a silent record of its own past movements. If a listener could somehow exist in that far future, they would hear the fading chorus of galaxies merging, stars collapsing, and black holes combining. Long before that time arrives, the legacy of collisions will also remain in the elements themselves. The carbon in every living being, the oxygen that fills the air, the iron that strengthens worlds, all were created in the furnaces of stars and distributed through galactic mergers. Those elements will endure long after life, planets, and even stars are gone. They will remain part of whatever structures the universe still allows, bonded into dust, drifting across the dark as the last tangible evidence of creation. Even the cosmic web, the largest structure ever formed, owes its existence to collisions. Where filaments crossed and galaxies gathered, mergers shaped the growth of clusters, which in turn anchored the geometry of space on the largest scales. This network, invisible but fundamental, defines how matter and energy are distributed even now. As the universe continues to expand, that pattern will fade from visibility but not from existence. It is frozen into space-time, a ghostly scaffolding that persists beyond light. The universe's future observers, if any could exist, would find themselves in a cosmos stripped of visible reference points. Yet, through mathematics, they might infer what once was. The background radiation, stretched to unimaginable wavelengths, would still carry the faintest memory of heat from ancient times. The uniform distribution of matter would hint at the processes that once created variety. Even in silence, the universe's history would remain encoded in its structure, its curvature, density, and residual motion. From a human perspective, it is easy to see this as an ending, but on cosmic scales, it is a transformation towards simplicity, the same process that has always guided the universe. Collisions are not accidents, they are mechanisms of renewal. Each merger redistributes energy, balances momentum, and reduces disorder in the long run. The apparent violence of galaxies crashing together is the universe's way of reaching equilibrium, a slow settling into harmony. The legacy of those collisions extends into meaning as well. They remind us that everything, no matter how vast or enduring, is part of a continuous exchange. Our solar system, our planet, and our existence arose because galaxies collided, mixing their elements and igniting new stars. Without those encounters, the ingredients for life would never have gathered in one place. Every breath we take, every molecule we touch, carries the distant imprint of forces older than time itself. In the end, what remains after collisions is not destruction but order. The chaos of motion gives way to the simplicity of balance. Space retains the shapes once carved by galaxies, and gravity remembers their movements even when matter is gone. The universe's final act is not silence born of loss, but rest achieved through completion. What was once turbulent becomes calm, what was once bright becomes subtle, and in that quiet transformation lies the enduring legacy of everything that ever collided, merged, or shone. At the end of its long journey, the universe will not end with a flash or a collapse. It will end quietly. Matter, energy, and motion will reach a state of near perfection, balanced, uniform, and still. The same laws that shaped galaxies and guided stars will continue to hold, even as time stretches beyond meaning. What remains will not be silence in the sense of nothingness, but silence as completion. The universe, after eons of change, will finally rest in its own equilibrium. From the first collisions of hydrogen clouds to the merging of galaxies, everything has been part of a single, unfolding process. Energy has moved, transformed, and spread, always conserving itself. Every particle has followed the rules written into nature since the beginning. Even when the last black holes vanish and the final photons drift through darkness, the logic of physics will endure. The universe will have become the pure expression of its own order, all motion balanced, all forces resolved. If you're still awake, you might think of this not as an ending, but as a kind of universal sleep. The cosmos has traveled through its bright and busy youth, through its creative middle age of stars and collisions, and into a calm beyond measure. Just as your body slows when rest arrives, the universe too will settle, its restless expansion softening into near stillness. Sleep, after all, is not the absence of life. It is its recovery, its return to balance. The same principle holds for the cosmos. In that far, cold age, space will no longer sparkle with light, yet it will still carry memory. The patterns shaped by galaxies will remain etched into the curvature of space-time. The background radiation, stretched until its waves span entire galaxies, will still hum faintly with the echo of creation. The universe will remember, in its quiet geometry, every movement that ever occurred. Even when light fades, information remains. Nothing that has happened is ever truly lost. From our perspective, living in a universe still full of brightness, this distant stillness is impossible to imagine. And yet, it is the inevitable result of the same stability that makes existence possible now. The calm future of the cosmos is written in the same equations that keep the moon in orbit and the atoms in balance. The universe's rest will not be death, but endurance, the continuation of law without the need for change. Astronomers and physicists who study this final era often describe it as the universe's last equilibrium. The expansion will slow but never reverse. Entropy will rise until no more work can be done. Yet even that condition is dynamic in its own way. Particles will still move, though faintly. Space will still expand, though imperceptibly. The universe will never truly stop. It will breathe at the slowest possible rhythm, a heartbeat stretched across eternity. That image carries a quiet comfort. Everything that has ever existed, every galaxy, every star, every thought, has been part of this continuum. Nothing has been wasted. Every transformation has contributed to the whole. We are temporary, but we are part of something that does not vanish. The atoms in your body were forged in stars that collided, in galaxies that merged, in a universe that continues to evolve. Even when sleep comes, those atoms keep moving, bound to the same cosmic rhythm that guides galaxies. So as you lie there, listening, breathing, perhaps feeling your mind drift, remember that stillness and motion are not opposites. They are the same phenomenon, seen from different moments in time. The universe does not resist its own rest. It welcomes it. And like the universe, you do not need to chase stillness. It will come naturally, as gravity brings planets to their paths, as galaxies find balance after chaos. The cosmos rests, not because it ends, but because it has found peace in its own persistence. And so too, may you, we from Sleepy Stories, wish you a good night.